You are looking at the night sky right now, maybe through a telescope, maybe just with your eyes. Either way, you feel it, that sense of vastness, of endless possibility, of a cosmos waiting to be discovered. And you believe, because you have been told, that with enough time and enough technology, humanity will eventually map it all. Every star, every galaxy, every corner of existence. But what if I told you that most of the universe is already gone? Not destroyed, not hidden, simply unreachable, forever. What if the light from most of what exists will never touch your eyes, no matter how long you wait? What if the universe is not revealing itself to you, but slowly, steadily, pulling a curtain across its face? And what if, in a few 100 billion years, future astronomers will look up and see almost nothing at all and have no way of knowing that anything else ever existed? This is not a metaphor. This is physics. And by the end of this video, you will never look at the night sky the same way again. When you look up at the stars, you are not seeing the universe as it is. You are seeing the universe as it was. This distinction matters more than you might think, and it forms the foundation of everything that follows. Light travels fast, unimaginably fast, at 299,792 kilometers per second. It crosses the distance from the moon to Earth in just over 1 second. It spans the gap from the sun to our planet in about 8 minutes. From this perspective, light seems instantaneous, a messenger that delivers information from across the cosmos in the blink of an eye. But even at this blistering speed, light is finite. It takes time, and across cosmic distances, that time becomes significant. It becomes everything. When you observe the Andromeda Galaxy, our nearest large galactic neighbor, you are seeing it as it appeared 2.5 million years ago. The light you are absorbing tonight left Andromeda when our ancestors were still learning to walk upright on the African savanna. Homo habilis had not yet emerged. The tools that would define early humanity had not been invented. And yet, that ancient light, carrying an image of a galaxy as it existed in the deep past, is only now completing its journey to your eyes. That galaxy has been doing things for 2.5 million years that you cannot yet know about. It might have changed dramatically. Stars might have exploded in spectacular supernovae. New stars might have formed from collapsing clouds of hydrogen. Civilizations might have risen, built great works, and fallen into dust. You would have no idea. You are watching a movie filmed before your species existed. Now extend this principle further. When astronomers point the Hubble Space Telescope at a distant galaxy cluster, they might see objects 5 billion light-years away. That light left its source when the Earth was still forming from the protoplanetary disk around the young sun. When the James Webb Space Telescope captures images of galaxies 13 billion light-years away, it is photographing the universe in its infancy, when the cosmos was less than 1 billion years old, when the first stars were just beginning to ignite. We are not observers of the present. We are archaeological observers, sifting through ancient light to reconstruct a past we can never visit. Every telescope is a time machine, and the further we look into space, the deeper we peer into history. This seems intuitive enough. Light takes time. We see the past. Most people accept this without much trouble. It is a fascinating quirk of the universe, a reminder that the cosmos operates on scales far beyond human intuition. But here is where it gets strange. Here is where the comfortable assumptions start to crack. The universe is 13.8 billion years old. We know this from multiple independent lines of evidence. the cosmic microwave background radiation, the ages of the oldest stars, the expansion rate of the cosmos traced backward to a single point. So you might assume that the farthest we could possibly see is 13.8 billion light years in any direction. After all, if the cosmos began 13.8 billion years ago, light could not have traveled farther than 13.8 billion light years since then. Reasonable logic, simple math. Completely wrong. The observable universe extends approximately 46.5 billion light years in every direction. That gives us a sphere roughly 93 billion light years across, in a universe that is only 13.8 billion years old. Let that sink in for a moment. We can see objects that are now 46 billion light years away, even though the universe has only existed for 13.8 billion years. This is not an error. This is not a typo. This is the actual measured size of the observable cosmos. How is this possible? How can we see further than light should have been able to travel? The answer reveals the first great limitation on our cosmic vision, and it is a limitation most people have never properly understood. It is a limitation that changes everything. Space itself is expanding, not into anything, not through anything. Space, the fabric of reality, the stage on which all cosmic events play out, is stretching. And it has been stretching since the beginning. Think of it this way. Imagine you are an ant standing on the surface of a balloon. You want to walk to another ant on the opposite side of the balloon. You set off, moving at your maximum ant speed. But as you walk, someone is inflating the balloon. The rubber stretches beneath your feet. The distance between you and that other ant grows faster than you can cover it. You are moving forward, making progress, but the goal is receding. Now replace the balloon with the universe. Replace the ants with galaxies. Replace walking with the speed of light. When the cosmic microwave background radiation was released, about 380,000 years after the Big Bang, the matter that emitted it was not 46 billion light years away. It was much, much closer. The universe was smaller then. Everything was packed together more tightly. But in the 13.8 billion years since that moment, space has expanded enormously. That matter, the same matter that released the ancient light we now detect as microwave radiation, has been carried away by the stretching of space itself. It has been riding the expansion like a surfer on an endless wave. Today, it sits approximately 46.5 billion light years away. The light did not travel 46.5 billion light years. The light traveled for 13.8 billion years. But the starting point moved during the journey. The universe stretched beneath the traveling photons, adding distance that the light did not have to cross. This is not a violation of relativity. Nothing is moving through space faster than light. Space itself is growing, and that growth has no speed limit. Einstein's cosmic speed limit applies to objects moving through space, not to space itself. And this is where the comfortable assumption breaks down entirely, because this expansion is not static, it is not gentle, it is not slowing down, it is accelerating. Before we delve deeper into what this acceleration means, let us pause to appreciate just how strange this finding is. For most of the universe's history, gravity was winning. The mutual attraction of all the matter in the cosmos was doing exactly what you would expect, pulling things together, slowing the expansion, working to reverse the outward rush of the Big Bang. For the first several billion years after the Big Bang, the universe was matter-dominated. The density of matter was high enough that its gravitational pull significantly affected the expansion rate. If you could have measured the expansion back then, you would have seen it decelerating, just as a ball thrown upward decelerates as Earth's gravity pulls it back. But dark energy was always there, even in those early eons. It just was not the dominant force. Dark energy's influence depends on the volume of space, not the density of matter. In a smaller, denser universe, matter won. Its gravity overpowered the repulsive effect of dark energy. But as the universe expanded, matter spread thinner. Galaxies moved apart. The average density of matter dropped, and dark energy, maintaining its constant density per unit volume, slowly gained the upper hand. Somewhere around 5 to 7 billion years ago, the balance shifted. Dark energy became the dominant component of the universe. The deceleration ended. The acceleration began. We are living in the aftermath of that transition. We are living in the dark energy era, the epoch when the expansion of the universe is running away faster and faster with no end in sight. This is not a gradual shift. This is not a minor adjustment to the cosmic trajectory. This is a fundamental change in the nature of the universe's evolution. For most of cosmic history, the universe was becoming more structured, more complex. Gravity was building galaxies and clusters, weaving the cosmic web of filaments and voids that we observe today. But now, that process is ending. Dark energy is pulling things apart faster than gravity can pull them together. On the larger scales, structure formation has ceased. The cosmic web is frozen, and slowly, inevitably, the threads of that web are being stretched to invisibility. We caught the universe at a moment of transition, a few billion years earlier, and we would have seen a decelerating cosmos, with no hint of the dark energy that would eventually dominate. A few billion years later, and we would have seen an accelerating cosmos, but with less evidence of what came before. We are poised at the pivot point, able to see both the past and the future of cosmic evolution. We are the witnesses to a changing universe, a cosmos in the process of transforming from a matter-dominated, structure-building era to a dark, energy-dominated dissipation era. This is another aspect of our cosmic luck. Not only are we living in the epoch when the evidence is visible, but we are living at the precise moment when the nature of that evidence is changing. We can see the transition happening. We can measure it. We can understand it. Future observers will not have this privilege. They will live entirely within the dark energy era with no memory of what came before. In 1998, 2 independent teams of astronomers made a discovery that shattered everything physicists thought they knew about the fate of the universe. It was, by any measure, one of the most shocking findings in the history of science. They were studying type ER supernovae, a particular kind of stellar explosion that serves as a cosmic yardstick. These supernovae occur when a white dwarf star, the dense remnant of a sun-like star, accumulates enough matter from a companion to push it over a critical mass limit. The white dwarf can no longer support itself against gravity. It collapses, and then it explodes. The key feature of type Ia supernovae is their consistency. Because they all explode at roughly the same mass threshold, they all release roughly the same amount of energy. They all have roughly the same intrinsic brightness. This makes them what astronomers call standard candles. If you know how bright something actually is, and you measure how bright it appears to be, you can calculate how far away it is. A 100-watt light bulb in your room is blinding. The same bulb a mile away is a faint point of light. distance dims things in a predictable way. The two teams, the Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt at the Australian National University and Adam Rees at Johns Hopkins University, were hunting for distant supernovae to measure the expansion history of the universe. The expectation was straightforward, based on decades of established physics. Gravity should be slowing the expansion of the universe. Every galaxy pulls on every other galaxy. The mutual attraction of all the matter in the cosmos should be acting like a brake, gradually decelerating the outward rush that began with the Big Bang. Think of throwing a ball straight up into the air. Gravity pulls it back. It slows down. Eventually, it stops and falls. The universe, most physicists assumed, was doing something similar. The expansion was coasting, gradually decelerating under the influence of gravity. The only question was whether it would eventually stop and reverse, collapsing back into a big crunch, or whether it would expand forever, gradually slowing but never quite stopping. But that is not what the data showed. The distant supernovae were dimmer than expected. Not slightly dimmer, significantly dimmer. The light had traveled further than it should have. The universe had expanded more than the models predicted. There was only one explanation that fit the observations. The universe was not slowing down. It was speeding up. The expansion of the cosmos was accelerating. When Perlmutter, Schmidt, and Rees published their results, the physics community was stunned. The finding contradicted intuition. It contradicted expectation. It seemed almost impossible, but the data was clear, and subsequent observations have only strengthened the conclusion. In 2011, the three astronomers were awarded the Nobel Prize in Physics for this discovery, which revealed that approximately 68% of the total energy content of the universe consists of something we cannot see, cannot detect directly, and do not understand. We call it dark energy. Dark energy is not dark matter. Dark matter is something else entirely, an invisible form of mass that holds galaxies and galaxy clusters together through gravity. We know dark matter exists because we can see its gravitational effects. Galaxies rotate too fast to be held together by their visible matter alone. Something invisible is providing extra gravity. That is dark matter. Dark energy is stranger, far stranger. Dark energy does not attract. It repels. It acts like a kind of anti-gravity, a pressure built into the fabric of space itself that pushes everything apart. And unlike matter, which dilutes as the universe expands, dark energy appears to maintain a constant density. As space expands, more dark energy comes into existence. The more space there is, the more dark energy there is, and the more dark energy there is, the faster the expansion accelerates. It is a runaway process, a cosmic feedback loop that cannot be stopped. Albert Einstein, in a moment of what he later called his greatest blunder, once added a term to his equations of general relativity called the cosmological constant. It was a fudge factor inserted to balance gravity and keep the universe static, because in 1917, everyone assumed the cosmos was eternal and unchanging. When Edwin Hubble discovered the expansion of the universe in 1929, Einstein abandoned the cosmological constant, embarrassed that he had missed the prediction that his own equations were making. But the universe, it seems, did not abandon it. The cosmological constant, or something very much like it, appears to be real. Space contains energy, empty space, vacuum, what we think of as nothingness, and this vacuum energy is driving the cosmos apart with ever-increasing ferocity. Think about what that implies. Really think about it. Every second, the space between distant galaxies grows, not because the galaxies are flying through space like shrapnel from an explosion, but because new space is being created between them. The fabric of the universe is stretching, and this stretching is accelerating. Galaxies that are far enough away are receding from us faster than the speed of light. This sounds impossible. This sounds like it should violate everything we know about physics. But it does not, because the galaxies are not moving through space faster than light. The space between us and them is simply growing faster than light can cross it. And this has consequences that most people never consider. Consequences that are, when you truly understand them, existentially terrifying. There is a boundary in the universe, an invisible line drawn across the cosmos that you cannot see, cannot touch, and cannot cross. Beyond this line, anything that exists is forever beyond your reach. Light emitted that will never reach you. Signals sent there will never arrive. No matter how long you wait, no matter what technology you develop, no matter how desperately you want to know what lies beyond, you will never, ever find out. This boundary is called the cosmic event horizon. Today, it sits approximately 16 billion light years away. Any galaxy beyond this distance is receding from us so quickly due to the expansion of space that photons it emits right now will never bridge the gap. The distance between us grows faster than light can travel. The photons will fly toward us at the speed of light, making progress, covering ground, but they will never arrive. The expansion will always win. But wait, we said earlier that we can see objects 46 billion light years away. How can we see things beyond the event horizon? Because we are seeing their past. This is crucial to understand. The event horizon defines what we can see from now. Light that is emitted today, at this very moment, from beyond 16 billion light years away, will never reach us. But light that was emitted in the past, when those objects were closer, when the expansion was slower, has had enough time to arrive. Consider a galaxy that is currently 30 billion light years away. The light we see from it today was emitted billions of years ago, when that galaxy was much closer to us, perhaps only 10 billion light years away. At that earlier time, the expansion rate was slower. The photons had a chance. They set off on their journey, and even though the space behind them was stretching, even though the galaxy was receding, they were moving fast enough to make progress. After billions of years, they finally arrived at Earth. So we see that galaxy. We see it as it was billions of years ago. We captured an image of its ancient self. But here is the unsettling part. We will never see that galaxy as it is now. We will never see it as it will be tomorrow. The light it is emitting at this very moment, the photons carrying information about its current state, will never arrive. They are already behind the event horizon. They have lost the race before it began. It is like receiving a letter from someone who has already died. The message comes from the past, describing a world that once was, but the sender is forever beyond your reach. You can read their words, but you cannot reply. You cannot visit. You cannot know what happened after the letter was sent. And it gets worse. Because the expansion is accelerating, the event horizon is effectively shrinking. Not shrinking in absolute terms, but shrinking in terms of what it includes. More and more galaxies are being pushed across this threshold. Objects that were once within our causal reach are slipping away. Think about a specific galaxy, one that is currently just inside our event horizon. Right now, just barely. Light emitted from that galaxy can eventually reach us. But as dark energy continues to accelerate the expansion, that galaxy will be pushed over the edge. Tomorrow, or next year, or next century, it will cross the threshold. And once it does, it is gone forever. Cosmologists Tamara Davis and Charles Lineweaver, working at the University of New South Wales, demonstrated something remarkable in their 2003 paper on superluminal recession velocities. We can currently observe galaxies that are receding from us faster than the speed of light. This sounds impossible, but it is not. The speed limit of relativity applies to objects moving through local space, not to the rate at which space itself can expand. A galaxy beyond a certain distance, roughly where the recession velocity exceeds the speed of light, is moving away from us superluminally right now. And yet we see them. We see the light they emitted long ago, when the expansion was slower, when space had not yet stretched their photons beyond our reach. According to Davis and Lineweaver, in all viable cosmological models, galaxies above a redshift of about 3 are receding faster than the speed of light right now. We observe thousands of such galaxies. We photograph them with Hubble and Webb. We study their spectra and measure their chemistry, and all of them are moving away from us at speeds that exceed the cosmic speed limit, carried by the expansion of space itself. But with each passing moment, we lose a little more. The universe we can observe is shrinking, even as the universe itself grows. The boundary is closing in. The walls are tightening. This is the first prison wall closing around us. The expansion of space is building a barrier that no technology, no ingenuity, no warp drive or wormhole or physics breakthrough can overcome. The laws of the universe itself are sealing us inside an ever-diminishing bubble of visibility. And we have not even reached the worst part yet. Imagine you are a scientist in the year 100 billion CE. You are intelligent, curious, equipped with instruments 1,000 times more sophisticated than anything we have today. Your civilization has survived unimaginable spans of time. You have mastered technologies we cannot even conceive. You have asked all the questions we are asking, and many more besides. You look up at the night sky. What do you see? Almost nothing. This is not speculation. This is not science fiction. This is a prediction, based on physics we understand today, made by serious cosmologists using well-established equations. In 2007, physicists Lawrence Krauss of Arizona State University and Glenn Starkman of Case Western Reserve University published a paper in the journal General Relativity and Gravitation, titled The Return of a Static Universe and the End of Cosmology. Their conclusions were haunting. In about 100 to 150 billion years, assuming dark energy remains constant at its current value, every galaxy outside our local group will have crossed the cosmic event horizon. The Milky Way and Andromeda, which are gravitationally bound to each other and will merge long before then into a single giant elliptical galaxy, sometimes called Milkomeda, will remain. A handful of small satellite galaxies, also gravitationally bound, will survive the crossing. Everything else will be gone, not destroyed. The galaxies will still exist. Stars will still burn. Planets will still orbit. Perhaps civilizations will still flourish, asking their own questions about the cosmos. But from our perspective, from the perspective of any observer in what remains of our local island of galaxies, they will have vanished completely. The light from these distant galaxies will have redshifted so dramatically, stretched by the expansion to such extreme wavelengths, that it will become undetectable. The photons will eventually have wavelengths longer than the observable universe itself. They will carry so little energy that no conceivable instrument could register their presence. The night sky will go dark, not immediately, not all at once, but steadily, inexorably, galaxy by galaxy. The universe will fade from view. Astronomers in that distant era will observe only their local island of stars, this single merged supergalaxy floating in an infinite, empty void. Everything else will be gone, invisible, unreachable, as if it had never existed. But the truly terrifying implication of Krauss and Starkman's work is not the darkness. It is not the loneliness of that far future. It is the ignorance. Those future scientists will have no way of knowing that anything else ever existed. Think about what we know today. We know the universe is expanding because we can see distant galaxies and measure their redshifts. Edwin Hubble made this discovery in 1929 by observing that nearly all galaxies are moving away from us, and that more distant galaxies are moving away faster. This redshift distance relationship is the foundation of observational cosmology. In 100 billion years, there will be no distant galaxies to observe. Every galaxy will have crossed the horizon. There will be no redshifts to measure because there will be no light arriving from distant sources. The most fundamental observation in cosmology, the observation that revealed the expanding universe, will be impossible to make. We know the universe had a hot beginning because we can detect the cosmic microwave background radiation, the afterglow of the Big Bang. This radiation fills all of space, a faint glow at a temperature of 2.725 Kelvin, just a few degrees above absolute zero. It was released when the universe was about 380,000 years old, when the hot plasma of the early cosmos cooled enough for atoms to form and for light to travel freely. In 100 billion years, this radiation will have redshifted beyond detection. The wavelengths will have stretched so much that they will be longer than any practical measuring device. The temperature will have dropped to effectively zero. The cosmic microwave background, the single most important piece of evidence for the Big Bang, will be erased. We know about the primordial production of light elements, the Big Bang nucleosynthesis that created hydrogen, helium, and trace amounts of lithium in the first few minutes after the universe began. The ratio of hydrogen to helium in the universe, about 75% to 25% by mass, is a direct prediction of the Big Bang model. No process in stars could have produced this ratio. It is a fingerprint of the universe's fiery birth. In 100 billion years, stars will have processed most of this primordial material. Hydrogen will have been fused into heavier elements through billions of years of stellar burning. The primordial signature will be diluted, confused, indistinguishable from the products of stellar nucleosynthesis. The evidence of Big Bang nucleosynthesis will be gone. Every pillar of modern cosmology will be knocked down, not by ignorance, not by lack of effort, not by any failure of intelligence or technology, by the physics of an expanding universe. Krauss and Robert Scherer expanded on this analysis in a 2007 paper titled The End of Cosmology, published in Scientific American. They calculated specific timescales. By 100 billion years, the redshift of receding galaxies will exceed 5,000, making them undetectable. By 10 trillion years, even the highest energy cosmic rays will have redshifted so much that their wavelengths will exceed the size of the observable universe. Future astronomers will look at their static island universe, this single merged galaxy floating in an infinite void, and they will conclude, quite reasonably based on all available evidence, that it is all that exists, that it has always existed, that the universe is eternal and unchanging. They will be wrong, completely, fundamentally wrong, but they will have no evidence to tell them so. Think about what that means. Really sit with it. Right now, in this brief window of cosmic history, we can see the evidence of the Big Bang. We can measure the expansion. We can detect the cosmic microwave background. We can observe billions of galaxies and understand that we are part of something unimaginably vast. But this knowledge has an expiration date. We happen to exist in the one epoch when the universe is willing to reveal its secrets. Before us, the universe was too young, too hot, too opaque to see clearly. For the first 380,000 years, the cosmos was filled with plasma, an ionized gas that scattered light and made the universe opaque. No observer could have seen more than a few light years in any direction. After us, the universe will be too empty, too dark, too expanded to observe. The evidence will be gone. We are the lucky ones, and we did not even know it until we worked out the physics of what is coming. But let us return to the present. Let us talk about what we can see, here and now, in this privileged epoch of cosmic visibility, and why even that is far less than you might imagine. The observable universe contains, by current estimates, somewhere between 200 billion and 2 trillion galaxies. This enormous range reflects the difficulty of counting objects that span such a vast range of sizes and brightnesses, many of which are too faint and distant to detect directly. In 2016, a study led by Christopher Consolis at the University of Nottingham used deep field observations from the Hubble Space Telescope and sophisticated mathematical models to estimate the total number of galaxies. The team converted Hubble images into three-dimensional maps, counted galaxies at different distances and different epochs, and then extrapolated to account for galaxies too small and faint to observe. Their conclusion: the observable universe contains at least 2 trillion galaxies, about 10 times more than previous estimates. Most of these are small dwarf galaxies, much smaller than the Milky Way, that existed in the early universe and have since merged into larger structures. When we look at the nearby universe, we see mostly large galaxies. When we look at the distant universe, we see the past, when galaxies were more numerous but smaller, 2 trillion galaxies, each containing, on average, somewhere between 100 million and 400 billion stars. That gives us somewhere between 200 sextillion and a septillion stars in the observable universe. Written out, a sextillion is 200,000, 1,000. These are numbers that the human brain is not equipped to comprehend. And this is just what we can see. Remember, the observable universe is defined by the cosmic horizon, the limit of how far light has traveled since the Big Bang. It is a sphere centered on Earth, not because Earth is special, not because we are at the center of anything, but simply because Earth is where we are. An observer in the Andromeda Galaxy would have their own observable universe, a sphere centered on them, overlapping with ours but not identical. An observer on the far side of the cosmos would have a completely different view. Beyond our observable sphere, there is more universe. How much more? No one knows for certain. The universe could be finite, wrapping around on itself in some higher dimensional topology that we cannot directly perceive. Or it could be infinite, extending forever in all directions, filled with galaxies and stars without end. But the theory of cosmic inflation provides a terrifying estimate. Inflation was proposed in 1980 by physicist Alan Guth, then at Cornell University, and now at MIT. The idea came from Guth's work on grand unified theories of particle physics, and it addressed several deep problems with the standard Big Bang model. The Big Bang model, on its own, cannot explain why the universe is so uniform on large scales. The cosmic microwave background radiation, the oldest light in the universe, has the same temperature in every direction to 1 part in 100,000. But in the standard model, regions on opposite sides of the sky were never in causal contact. Light had not had time to travel between them. They should not have had time to equilibrate. Why are they the same temperature? Inflation solves this problem. The idea, later refined by Andre Linde at Stanford, Paul Steinhardt at Princeton, and others, suggests that in the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Not the gradual stretching we observe today. Violent, explosive, incomprehensibly rapid growth. In approximately 10 to the minus 32 seconds, a time span so short that human language has no words for it, the universe expanded by a factor of at least 10 to the 26th power. A region smaller than a proton expanded to something larger than the entire observable universe today. Every part of the cosmos we can now see was once packed together in a region so small that light had plenty of time to equilibrate the temperature. If inflation is correct, and there is substantial evidence supporting it from observations of the cosmic microwave background and the large-scale structure of galaxies, then the total universe is incomprehensibly larger than the observable universe. Estimates vary depending on the specific model, but some calculations suggest the whole universe could be at least 10 to the 23 times larger than what we can see. That number is so large that comparisons become meaningless. But let me try. Imagine the observable universe is a single grain of sand. On this scale, the total universe might be larger than the Earth. It might be larger than the solar system. It might be larger than our entire galaxy. We are looking at a grain of sand and wondering about the beach. And we will never, ever see the rest of it. Not because we lack technology. Not because we are not trying hard enough. Not because we are not clever enough. Because the light from those regions has not had time to reach us since the Big Bang, and due to the accelerating expansion, it never will. We are marooned on an island in an infinite ocean, and the ocean is receding faster than any boat could ever sail. The island is shrinking, the horizon is closing in, and there is no rescue coming. Perhaps you are thinking, surely there must be some way around this, some loophole in the physics, some clever trick that could let us see further, reach beyond the horizon, glimpse the unreachable universe. Scientists have considered the options. Theorists have explored every conceivable avenue. None of them work. Wormholes? The theoretical tunnels through space-time that appear in Einstein's equations of general relativity? They are mathematically possible, but they require exotic matter with negative energy density to hold them open. No such matter has ever been observed. Every experiment designed to detect it has come up empty. And even if wormholes could be created and stabilized, they could not take you beyond the cosmic horizon. The horizon is not a place. It is not a wall floating in space that you could tunnel around or drill through. It is a boundary in time and causality. It defines the regions of space-time that can send signals to us. Regions beyond the horizon are causally disconnected. There is no there to travel to, because there and here cannot exchange information. They might as well be in different universes. Faster than light travel? The Alcubierre warp drive, proposed in 1994 by Mexican physicist Miguel Alcubierre, describes a space-time geometry in which a bubble of flat space moves faster than light by contracting space in front of it and expanding space behind it. The ship inside the bubble would not be moving through space faster than light. Space itself would be moving. It is a beautiful idea, and it is almost certainly impossible. The Alcubierre drive requires negative energy density on a massive scale, the same exotic matter that wormholes would need. It creates insurmountable problems with causality, potentially allowing for time travel and all the paradoxes that entails. And even if you could build one, you would still be limited by the cosmic horizon, because the horizon is not defined by where you can travel, but by what signals can reach you. Waiting for the expansion to slow? Maybe dark energy will weaken over time? Maybe the acceleration will eventually stop. The evidence suggests otherwise. Observations from the Dark Energy Spectroscopic Instrument, a massive project mapping millions of galaxies to study the expansion history of the universe, have found hints that dark energy may actually be changing over time. But the change, if real, is not towards slowing down. Some analyses suggest dark energy may be increasing, accelerating the expansion even faster. And even if dark energy somehow turned off tomorrow, the damage is already done. Galaxies that have crossed the event horizon are gone. The light they are emitting will never reach us. You cannot undo a horizon crossing. The prison is real. The walls are closing, and there is no door. Some physicists have speculated about more exotic possibilities. Perhaps we live in a multiverse, a vast collection of separate universes, each with its own physical laws and constants. Perhaps our observable universe is just one bubble in an infinite foam of cosmic bubbles, each forever isolated from the others. If this is true, then the situation is even more extreme than what we have described. Not only can we not see beyond our cosmic horizon, but there may be entire other realities, other modes of existence, other versions of physics that we can never access or even detect. The prison would have prisons within it, each sealed off from all the others, each containing observers who believe their bubble is all there is. This is speculative physics, not established science. We have no direct evidence for a multiverse. We may never have such evidence by the very nature of the concept. But the possibility haunts cosmology, a reminder that our ignorance may be even deeper than we know. And then there are the questions we have not even thought to ask. Throughout history, scientific progress has repeatedly revealed that the universe is stranger, larger, and more complex than previous generations imagined. The Earth was not the center of the cosmos. The Sun was not the only star with planets. Our galaxy was not the only galaxy. The universe had a beginning. Space and time are intertwined. The vacuum is not empty. Each of these discoveries came as a surprise. Each of them overturned confident assumptions. Each of them expanded our understanding in directions we hadn't anticipated. What assumptions do we hold today that will seem naive to future scientists? What questions are we failing to ask because we lack the concepts to frame them? What aspects of reality are we missing? Not because the evidence is hidden, but because we do not know how to look. The history of science suggests that there is always more, always another layer, always a deeper truth waiting to be uncovered. But the expanding universe places a limit on this process. There may come a time, perhaps has already come a time, when some truths become physically inaccessible, when the evidence has redshifted away, when the signal has faded below any possible detection threshold, when the answers exist but can never be reached. We do not know how many such truths there are. We do not know what we have already lost. We do not know what we are about to lose. We only know that the universe is vast beyond comprehension, that most of it is beyond our reach, and that the part we can see is shrinking with every passing moment. This brings us to perhaps the most disturbing realization of all, one that forces us to confront the nature of knowledge itself and our place in the cosmic story. What else might we be missing? If the future scientists in 100 billion years will be fundamentally unable to discover the Big Bang, unable to know about the expansion, unable to detect the existence of other galaxies, then their picture of the universe will be completely, catastrophically wrong. They will not know what they do not know. They will construct theories that fit their data, and those theories will be false. They will be brilliant scientists, perhaps far more intelligent than us, with instruments far more sophisticated than anything we can imagine. They will gather all available evidence with meticulous care. They will apply flawless logic to interpret their observations, and they will conclude with complete confidence that the universe is a static, eternal island of stars floating in an infinite void. They will be wrong about everything that matters. Could the same be true of us? We assume that we live in a special time, a cosmic sweet spot where the evidence happens to be visible. Krauss and Shatter, in their papers, explicitly make this point. We are fortunate to exist in the epoch when cosmology is possible, when the universe is willing to show us its history. But how do we know? How can we be certain that we are seeing everything that matters? What if there are aspects of the universe that were once detectable but are no longer? What if some cosmic evidence has already redshifted away? Some primordial signal has already faded below our detection threshold? What if there are phenomena that have not yet produced observable effects but will in the future? What if we are missing evidence that will only become apparent to observers millions or billions of years from now? The physics of horizons and expansion creates a kind of cosmic epistemological trap. You can only know what the universe allows you to know, and the universe is not obligated to be cooperative. Krauss and Starkman's work implies something unsettling. Observational cosmology is a time-limited endeavor. The universe does not owe us its secrets. It reveals what it reveals, when it reveals it, and then it moves on. We are not entitled to complete knowledge. We are not guaranteed the full picture. We might be cosmic goldfish, staring at the walls of our bowl, convinced we understand the ocean. There is no way to know what we are missing. That is the nature of a horizon. You cannot see beyond it, and you cannot know what lies there. You can only know that something does lie there, that the universe extends far beyond your vision, and that most of it will remain forever unknown. This is not a failure of science. This is a fundamental feature of reality. And yet, despite all of this, despite the shrinking horizon and the fading light and the incomprehensible vastness that will forever remain hidden, there is something remarkable about our situation, something that approaches the miraculous. We exist in the one moment when understanding is possible. Think about what that means. The universe is 13.8 billion years old. It will exist for trillions of years more, at least in some form. Stars will burn for another 100 trillion years before the last red dwarfs gutter out. Black holes will persist for unimaginable spans of time after that, slowly evaporating through Hawking radiation over timescales of 10 to the 100 years and beyond. And yet, of all the cosmic epochs that could contain conscious observers, we happen to be in the narrow window when the evidence is visible. The cosmic microwave background is detectable now. It will not be forever. We can measure it with exquisite precision. The Planck satellite mapped its tiny temperature fluctuations across the entire sky. The Wilkinson microwave anisotropy probe revealed the seeds of cosmic structure. The Atacama Cosmology telescope has given us the highest resolution images yet of this primordial light. These observations tell us about the universe when it was only 380,000 years old. They tell us about the density of matter and energy. They tell us about the geometry of space. They tell us about the initial conditions that gave rise to galaxies and stars and planets and us. In 100 billion years, this information will be erased, stretched into oblivion, gone forever. We can observe galaxies at the edge of visibility, seeing the universe when it was less than 1 billion years old. The James Webb Space Telescope is pushing this boundary further every month, capturing light from some of the first galaxies that ever formed. We are watching stars ignite for the first time, watching the universe emerge from darkness. In 100 billion years, these galaxies will have vanished. Their light will never arrive. No telescope, no matter how powerful, will be able to see them. We can see the web of cosmic structure, the filaments of galaxies stretching across hundreds of millions of light years, tracing the gravitational scaffolding of the universe. We can map the distribution of dark matter. We can measure the expansion rate at different epochs and reconstruct the history of cosmic acceleration. All of this will be gone, erased by expansion, lost to redshift, invisible to any future observer. But we are here, now, and we can see. There is a strange beauty in that, a privilege we did not earn and do not deserve. The universe has opened a window for us, briefly, before closing it forever. And in that light, for this fleeting moment, we can glimpse the truth of what we are and where we came from. There is something else we must consider, something that makes our situation even more poignant. The universe is not merely hiding its distant reaches from us. It is actively erasing the evidence of its own existence, piece by piece, moment by moment. Consider what happens to a photon traveling across the cosmos. It leaves a distant galaxy, flying toward us at the speed of light. Behind it, the galaxy continues to recede, carried by the expansion of space. The photon travels and travels, covering billions of light years, over billions of years. But as it travels, something happens to it. The photon is stretched. As space expands, the wavelength of light passing through it gets longer. Blue light becomes green, then yellow, then red, then infrared. Eventually, it becomes microwave radiation, then radio waves, then something so long wavelength that no instrument can detect it. This is called cosmological redshift, and it is not the same as Doppler shift. Doppler shift happens when a light source moves through space. Cosmological redshift happens because space itself is stretching while the light is in transit. The further light travels, the more it gets stretched. Light from the most distant galaxies we can see has been stretched so much that it arrives as infrared radiation, invisible to the human eye, but detectable by instruments like the James Webb Space Telescope. Light from the cosmic microwave background has been stretched by a factor of about -100 since it was emitted, turning from the orange glow of hot plasma into cold microwave radiation. And this stretching continues. It will continue forever, as long as dark energy drives the expansion. Eventually, the photons from distant galaxies will be stretched so much that their wavelength exceeds the size of the observable universe. They will carry so little energy that even a single quantum of their light could not register on any detector. They will become, for all practical purposes, non-existent. This is not merely a failure of technology. This is a fundamental physical limit. Information is being destroyed not by any deliberate process, but by the passive operation of cosmic expansion. The universe is forgetting itself, and we are watching it happen in real time. Every year, more galaxies cross the event horizon. Every year, more light redshifts beyond detection. Every year, the visible cosmos shrinks a little more, while the total cosmos grows incomprehensibly larger. There is a certain horror in this realization. We are not merely limited observers, catching a glimpse of something larger. We are observers on a sinking ship, watching the horizon rise around us as the waters close in. The universe is not opening itself to us. It is closing itself off, sealing away its secrets one by one, leaving us with an ever smaller window on an ever larger reality. But there is also, perhaps, a kind of grace in it, because we are here now, in the brief moment when seeing is possible. We are the witnesses. We are the ones who will know what was, even as it fades into unknowability. We are the memory of a universe that is forgetting itself. Future observers, if they exist, will have no way of knowing what they have lost. They will not miss the evidence of the Big Bang because they will never know it existed. They will not mourn the disappeared galaxies because they will never have seen them. Their ignorance will be complete and therefore painless. But we know. We can see the evidence. We can measure the expansion. We can calculate what will be lost and when. We are the generation that understands both what is visible and what will vanish. There is a weight to that knowledge, a responsibility, perhaps, to observe what we can while we can, to record it, to understand it, to appreciate it, because one day there will be no one left who can. Let us talk for a moment about what it feels like to confront these facts. Not the physics of them, but the existential weight. Human beings evolved on the African savanna, in small groups, with concerns that extended no further than the next hunt, the next season, the next generation. Our brains are not designed to comprehend cosmic scales. We think in terms of years, not billions of years. We think in terms of miles, not billions of light years. We think in terms of hundreds of people, not hundreds of billions of galaxies. When you read that the observable universe contains 2 trillion galaxies, something in your mind registers the number but does not truly process it. You cannot visualize 2 trillion of anything. The number is too large. It exceeds the capacity of human intuition. And when you learn that this observable universe, this impossibly vast sphere containing sextillions of stars and presumably quintillions of planets, might be a vanishingly small fraction of the total cosmos, something in you recoils. The mind rebels against such enormity. It seeks refuge in smaller, more comprehensible thoughts. This is natural. This is human. We are not equipped by evolution or by culture to grapple with the infinite. But there is something valuable in making the attempt. Because when you truly sit with these facts, when you let them sink past the intellectual surface and settle into your bones, something shifts. The concerns of daily life, the anxieties and frustrations and ambitions that consume so much of our attention begin to seem less urgent, not unimportant, but somehow smaller, more manageable. Seen against the backdrop of cosmic immensity, human problems retain their significance but lose their weight. This is not nihilism. It is not the conclusion that nothing matters because everything is small. It is something closer to the opposite, the recognition that we are part of something staggeringly vast, something that extends far beyond our comprehension, something that will continue long after we are gone. And within that vastness, our brief lives have a value that is not diminished, but somehow enhanced by the scale of what surrounds us. We are the universe become conscious of itself. We are matter that has arranged itself to look back at the stars and wonder. In all the cosmos, as far as we know, this is rare, perhaps vanishingly rare, perhaps unique. And we happen to exist in the one moment when understanding is possible. There is a gift in that. A responsibility, yes, but also a gift. Consider what we have accomplished in the brief time since we began to look outward. Just 4 centuries ago, Galileo pointed his telescope at the sky and saw mountains on the moon, moons around Jupiter, phases of Venus. He shattered the ancient belief in a perfect, unchanging heavens. He showed that the cosmos was a place, not a decoration. A century ago, we did not know that other galaxies existed. The spiral nebulae were thought to be gas clouds within our own Milky Way. It was Edwin Hubble, using the 100-inch Hooker telescope on Mount Wilson, who first proved that the Andromeda Nebula was in fact a galaxy far beyond our own, and that the universe was far larger than anyone had imagined. Half a century ago, we had never seen the cosmic microwave background directly. Arno Penzias and Robert Wilson, working at Bell Labs in 1965, stumbled upon it by accident while trying to eliminate noise from a radio antenna. They found a persistent hiss coming from every direction in the sky at a temperature of about 3 Kelvin. It was the afterglow of the Big Bang, the oldest light in the universe, and its discovery transformed cosmology from philosophy into precision science. A quarter century ago, we did not know that the expansion of the universe was accelerating. Dark energy was not part of our vocabulary. The fate of the cosmos was an open question, with most physicists assuming a gradual deceleration toward either eternal coasting or eventual collapse. And just in the last few years, the James Webb Space Telescope has shown us galaxies forming when the universe was only a few 100 million years old. We are watching the dawn of cosmic structure, the emergence of light from darkness, the first tentative steps towards stars and planets, and perhaps life. In 4 centuries, we have gone from not knowing that planets orbit the sun to photographing the birth of galaxies. In 4 centuries, we have expanded our vision from the naked eye sky to the edge of the observable universe. In 4 centuries, we have learned more about the cosmos than all previous generations of humanity combined. And we have done this in the brief window when such learning is possible. There will never be another epoch like this one. There will never be another time when the evidence is so abundant, so accessible, so rich with information about the origin and fate of everything. Future civilizations, if they exist in the far future, will have to make do with less, much less, eventually nothing at all. We are the golden age of cosmology. We are living through it right now. We will never see the whole universe. We will never know its full extent. The vast majority of existence is and will forever remain beyond our reach, sealed behind horizons that no technology can breach, hidden by physics that no ingenuity can circumvent. The numbers are almost impossible to grasp. The observable universe, this tiny bubble of visibility centered on our pale blue dot, contains perhaps 2 trillion galaxies. The total universe, according to inflation, might be 10 to the 23 times larger. If every observable galaxy were a grain of sand, the total universe would contain more grains than there are atoms in a star, and we will never see any of it. But we can see enough to know that it is there, enough to understand that our little bubble of visibility is not all there is, enough to feel the weight of the infinite pressing against the walls of the observable, reminding us that mystery is not a failure of science, but a feature of reality. The universe is not a puzzle to be solved. It is an ocean without shores, and we are standing on a beach that is slowly being swallowed by the tide. The night sky is not what you thought it was. Every star you see is a message from the past. Every galaxy is a time capsule, sealed and delivered across billions of years. And beyond those galaxies, beyond the farthest objects our telescopes can capture, there is more, so much more. Galaxies without number, stars beyond counting. Perhaps civilizations we will never meet, asking the same questions, staring at their own horizons, wondering what lies beyond. We cannot reach them. We cannot see them. We cannot know them. But we know they are there. And in that knowledge, in that humbling confrontation with the limits of the possible, there is something that feels very much like awe. Not the awe of conquest, of puzzles solved and mysteries conquered, but the awe of standing at the edge of an infinite shore, watching the waves recede, knowing that the ocean goes on forever. The universe is not hiding from us. It is not playing a cosmic game of keep away. It is simply too vast for us to contain, too old for us to witness, too fast in its expansion for us to catch. And perhaps that is the most profound truth of all. We are small, we are brief, our vision is limited, our reach is finite, and our time is short. But for this one moment, in this one place, in this one epoch of cosmic history, we can look up at the stars and understand that we are part of something so much larger than ourselves, something that began before us, that extends beyond us, that will continue long after we are gone. We cannot see the entire universe. We never will. But we can see enough to know it exists. We can see enough to understand our place in it. We can see enough to be filled with wonder at its scale and terror at our insignificance and gratitude for this brief window of sight. And that, somehow, is enough. The curtain is closing. The light is fading. The universe is pulling away, second by second, into an infinite darkness that will eventually swallow everything we know. But right now, in this instant, the stars are still visible. The galaxies are still glowing. The cosmic microwave background is still washing over us, carrying whispers of the beginning. Look up, look now, while you still can, because one day, for those who come after, there will be nothing left to see. Think about that final image. A scientist, billions of years from now, standing on a planet orbiting a star in the merged remnant of the Milky Way and Andromeda. They look up at the night sky with instruments far beyond anything we possess. They search for signals, for patterns, for any hint of what lies beyond their island of light. They find nothing, not because the universe is empty, not because they lack the technology, but because the light from everything else has faded beyond detection. The cosmic microwave background has stretched to wavelengths larger than their world. The other galaxies have redshifted into invisibility. The evidence of the Big Bang has been erased. They conclude, quite reasonably, that their galaxy is all there is, that it floats alone in an infinite void, that the universe has always been this way and always will be. They are wrong, but they have no way of knowing. And somewhere in their scientific literature, perhaps, there is a question that no one asks. What if there is more? What if we are missing something? What if the universe once held secrets that are now beyond our reach? But why would they ask that question? What evidence would prompt it? Their observations are complete. Their theories fit the data. There is no anomaly, no mystery, no hint of anything beyond. The universe has hidden itself from them, and it has hidden so well that they do not even know to look. We are different. We know. We can see the light that they will never see. We can measure the expansion that they will never detect. We can read the cosmic microwave background that will be erased before they are born. We are the keepers of a cosmic memory that will not survive us. And perhaps that is the deepest truth of this story. The universe is not ours to keep. It is not ours to understand completely. It is passing through our hands like water, visible for a moment, then gone. But in that moment, in this moment, we can look up and see. We can know that there is more. We can feel the weight of infinity pressing against the walls of our small, shrinking bubble of light. And we can be grateful, impossibly grateful, that we are here to witness it.